Good morning, everybody. Let me first thank the organizers for inviting me to present my work in this in this conference. So, I actually have been giving this talk of late in several conferences with overlapping participants. So, if you are hearing this talk for the second time or for the third time or for the nth number of times, so it's my apologies. Okay. So, today I will be talking about warm inflation. This is a variant scenario of the standard inflationary model, and I will explain what warm inflation is, and I will tell you that this warm inflation has some very novel and attractive features over the standard inflationary picture that people do talk about in general. Okay. So, of course, cosmic inflation, as you know, is a very brief period of the early universe when the universe had expanded exponentially, and the dynamics is definitely governed by Einstein's field equations, where this is the Einstein tensor and this is a matter which determines the evolution of this space time. And during inflation, this FRW metric has this scale factor sitting here, which is almost exponential, which is, oops, I went really far. Okay. So, this scale factor is exponential. Oh, the scale factor is exponential here, and this is almost, this Howell parameter is almost constant, and it depends very slightly on time. And on the right hand side, so what is the matter which can drive this universe, which can drive this universe to expand exponentially, is a slowly rolling scalar field, and this is very much needed because, as I will explain in my later slides, that if you have such a flat, very flat potential where the inflaton field is rolling over this flat region, only then you can drive this universe to expand exponentially and accelerate at that time. And at some point of time, inflation has to end, and the standard Big Bang evolution of the universe should start. So, what happens that at some point of time, this flat region should end and the inflaton field should start rolling faster, so that inflation can end. But the thing is that, as because the universe is expanding exponentially during inflation, when inflation ends, we are having a universe which is devoid of all matters and everything. So, you have to reheat a universe. How to reheat a universe? The standard picture is that the inflaton potential has this kind of a bottom of the potential where the inflaton field oscillates and reheats. Okay. So, this is the standard picture of inflationary scenario, and the flatness of this potential during inflation is measured by the slow roll parameters. As you can see, this epsilon is proportional to the first derivative of the potential and eta is proportional to the second derivative of the potential, and both has to be much smaller than 1, indicating that this region has to be very, very flat. Okay. So, I will come back to this picture again when I will be talking about warm inflation, and I will show you that this kind of a scenario is actually not needed in warm inflation at all, and that is one of the novel features of. So, you can see that basically you need a very constrained kind of a inflaton potential to have inflation. Okay. So, you cannot have any potential which can drive inflation in a standard picture. Okay. Now, let me talk about slightly about what is warm inflation. So, this warm inflation is something, so I already explained this picture for the standard inflation, which from henceforward I will keep mentioning as cold inflation. So, as I said that in cold inflation, you should have a flat region where inflation takes place, and when the potential becomes steep, inflation ends, and at the bottom of the potential the inflaton oscillates and reheats the universe. And this is the equation of motion of inflaton field during cosmic inflation, and this is basically nothing but a Klein-Gordon equation, except there is this factor sitting here, which is coming due to the background expansion of the universe. This acts like a friction term in the Klein-Gordon equation the general Klein-Gordon equation that people are used to seeing in particle physics. Okay. So this is a standard picture, but what is warm inflation? The warm inflation is saying that in cold inflation, basically this is a single field scenario where this inflaton field has no interactions and it's basically slowly rolling down its potential and expanding the universe. But in warm inflation, it is considered that this inflaton field has very strong interactions with other particles, so that this inflaton field can keep on dissipating its energy to a constant radiation bath and can maintain a constant radiation bath despite the exponential expansion of the background universe. Okay. So what is happening is that in cold inflation, when you have to reheat the universe, you actually need some kind of coupling of the inflaton field with matter so that it can dissipate its energy to the radiation bath. But while you are inflating the universe, you are ignoring all these couplings. But in warm inflation, you are not ignoring these couplings at all during inflation. You keep them effective and you keep, so basically it is reheating throughout. Okay. So when inflation ends, you actually have a constant radiation bath which can start a radiation dominated epoch, and so you do not need a separate reheating phase. So basically this kind of a potential where there should be a bottom of the potential where the inflaton should oscillate and reheat, that is not needed in warm inflation at all. Okay. And again, you actually do not need a very flat potential, even a very steep potential can be sustained in warm inflation. Okay. So also the equation of motion is changed. Now you have, so this is the dissipative term. So this is the term which is taking away energy and dumping into a radiation bath which is coexisting during inflation. So you can see this dissipative term also includes another friction term in the Klein-Gordon equation of motion. So now warm inflation, you have two kinds of friction term, one coming from the expansion of the background universe and one is coming from the dissipative term. So depending on which of these two dissipative terms are dominating the evolution of the inflaton field, one can categorize warm inflation into two categories. If this friction term is much smaller than the background friction term, then basically it is almost like a standard cold inflationary scenario, though you have a radiation bath maintained, but those kind of warm inflationary scenario is called weak dissipative models, and when this part dominates over this part, then of course the dynamics is quite different from the standard cold inflationary scenario, and you call that warm inflation is happening in a strong dissipative regime. Okay. So this is what is different between the standard cold inflationary picture and warm inflationary picture. So why should we talk about warm inflation? First of all, as I already told you that warm inflation does not require a reheating phase. Okay. So reheating is something which people are still struggling to understand, mainly because reheating does not leave much imprint on the CMB. Okay. So we do not know what kind of reheating process that universe has gone through if you believe in the standard cold inflationary picture, but warm inflation does not require that kind of a reheating phase. So that is one of the good points about warm inflation. The other thing is that the tensor spectrum is much more suppressed. It comes out to be when you do the perturbation analysis, the tensor spectrum is much more suppressed than in cold inflation. So the standard lambda phi 4 or lambda phi, m square phi square kind of potential which are generally ruled out in in standard cold inflation by the Planck data, you can make them accommodate in warm inflation, that because in warm inflation this kind of potentials does not produce that amount of tensor fluctuations. Okay. And there are other good reasons to consider warm inflation. First of all, in strong dissipative regime, it prefers small field inflation models, and we know that the present data prefer small field models. And warm inflation significantly elevates, if you try to build a supergravity model of inflation, then warm inflation can significantly alleviate the eta problem and gravity no problem. And of course, in 2018 and 19, there was quite a ruckus about swampland conjectures, and I showed that having warm inflation rather than cold inflation, it will help you get rid of the swampland conjectures and can have successfully inflation, one can embed inflation successfully in string model. So, I had written some series of paper on this topic, but I am not going to talk about this here today. But just look at just to give you an idea of where warm inflation stands today. This is the standard cold inflationary picture which was first proposed by Alan Guth. If you read this, that this line at least. So, of course, inflation was introduced to get rid of these fine tuning problems of the Big Bang universe, but then this Guth is writing that these problems would disappear if in its early history the universe supercooled to temperature 28 or more orders of magnitude below the critical temperature of for some phase transition. So, that is when if you have a standard inflationary picture, when inflation ends, you actually end up in a supercooled inflation. Okay? So, this is the standard picture and you can look at its citation. So, this is not the standard citation, I mean this is not a full citation. People when write inflationary papers nowadays, they do not even cite this paper. So, the citation should be much higher, but this graph is very interesting. So, you can see the interest in inflation is actually ever growing. So, nowadays people are writing nearly 500 papers per year, which is a good thing. So, this is even after 40 years of its proposal, this is a very active field of research. On the other hand, if you look at warm inflation and if you read, first of all read this abstract, what, so it is Barrera who proposed warm inflation after 15 years of, where when cold inflation was proposed by Guth. So, it is written that assuming a first order phase transition during inflation, a model scenario is described which does not require a tiny coupling of the inflaton field. Thermal equilibrium is closely maintained and no large scale reheating is necessary. So, this is, so this is the standard picture, but look at the citation. So, it first of all it is orders of magnitude less, but it also tells you that warm inflation is very less explored than the cold inflationary picture. And if you look at this graph, the inflation is, I mean the interest in warm inflation is also growing with time. So, if not hundreds of papers, but at least 50 papers per year is being written in warm inflation nowadays. Okay. So, today's topic is how inflation ends. So, I am going to talk about this graceful exit. So, and that is very important because you have to end inflation, and that is a very interesting in warm inflation. So, this is a dynamics. This is the Klein-Gordon, this is the Friedmann equations in standard cosmology, and you know if you have to accelerate universe, then you have to have a fluid with omega less than minus 1/3. So, cosmological constant which has omega minus 1 is a perfectly nice fluid which can give you exponential expansion, but the problem with cosmological constant is you will never get a graceful exit. On the other hand, if you have an inflaton field and let it slow roll means the potential energy has to dominate. So, if you let kinetic energy dominate, then it will give you a steep matter which will not inflate the universe. On the other hand, if you let this gradient term dominate, it will give you a matter with negative equation of state, but not enough to inflate. But if you let the potential dominate, it will definitely inflate, it will behave like a cosmological constant. But the good part is that this potential, when the inflaton field is slowly rolling over it, this equation state will evolve, and at some point of time it will become positive, and that time inflation end and you will achieve graceful exit. And of course, you need epsilon v to be much smaller than 1. And so, this is the kind of epsilon that you need to end inflation in the standard cold inflationary picture, that it should be growing with time. So, you need epsilon which is growing in time. So, n is just number of e-folds, is the one way of keeping time in exponential order. So, it is just treated as time. So, you basically, so at this point your gradient is much steeper. So, it will become, it will remain smaller in this region, and some point of time it will grow and end inflation. So, this is a very mundane way of ending cold inflation, and you need a very specific kind of potential also. On the other hand, warm inflation is very different. Warm inflation takes place when epsilon is much smaller than 1 plus q. Q is this ratio of this two dissipative term that was present in the inflaton equation of motion, and you can see that now the condition of having ending inflation is epsilon v is not equal to 1 but 1 plus q. Both epsilon v and q evolves in time. You can basically derive this equation with if you consider this kind of a dissipative term, and it is very easy to calculate, and you can see now both these two parameters is evolving in time. So, in how many ways you can achieve graceful exit in warm inflation? First of all, if you have a potential in which epsilon grows, in cold inflation you will always achieve a graceful exit in this kind of potential. So, let's first say if you have a warm inflation where q is constant, then definitely this is like cold inflation, but you are raising the bar from 1 to 1 plus q, and cold inflation will definitely end. On the other hand, if you have a warm inflation model where q is decreasing, then also you will end warm inflation. On the other hand, if you let q grow but with a smaller rate, then also you can exit warm inflation. On the other hand, if you let q to grow faster than epsilon, so even if you have a potential in which epsilon grows, in which cold inflation will always end, you will not achieve warm graceful exit in warm inflation. So, this is very interesting. Let us say if you have a potential where epsilon is constant, this is a classic case of this power law potential where epsilon remains constant, and you can never achieve graceful exit in cold inflation, but in warm inflation you can achieve this graceful exit if you have q decreasing. So, graceful exit in power law inflation is possible in warm inflation, which is not possible in cold inflation, and if you combine this this power law potential with this kind of upsilon, you will reach this kind of a scenario, okay, where you can gracefully exit from warm inflation. And if you have epsilon decreasing, then definitely cold inflation will never end, but warm inflation will end if you choose a model such that your q is decreasing faster than your epsilon, okay. So, these are very different ways of ending warm inflation. So, these graceful exit conditions put constraint on the combination of the inflaton potential and the upsilon that you can combine in warm inflation. So, as you can see that even if you have, let us say your C is 0 and P is minus 1, so epsilon is 1 upon T. So, if P is minus 1, then you can see that lambda phi 4 is not a good potential, because these white regions are where there is no graceful exit. So, there won't be any graceful exit in this region, okay. So, this definitely gives you a constraint on what kind of potential you can have, but I do not have time to get into this, so let me skip it. So, what I wanted to say that this background analysis of warm inflation is not a mundane task like in cold inflation, but it reveals the nature of the warm inflationary model itself, and it will give you constraint what kind of, even before you go and do your perturbation analysis, it will give you some hint what kind of potential goes with what kind of dissipative coefficients. So, thank you.
Thanks, Ratna. Questions? Yeah, Rajiv.
Yeah, so thank you for the nice talk. So I think in the case of slow roll inflation, there was a fine-tuning program from the viewpoint of effective field theory about the potential slow roll parameters. So do you have similar fine-tuning program?
Fine-tuning problem in the sense that
so there's
there are thermal corrections to the potential.
quantum correction to the potential usually.
Yes, yes. So there are people have constructed warm inflationary models where the thermal corrections are very less, or the quantum corrections to the potential are very less, and also you do not need a very flat potential to drive inflation. Even
yeah, but I have been always wondering is the universe is expanding rapidly.
Yes.
And you have to heat up. So
yes.
If you heat up too much, universe becomes too hot, and if you heat up
no, so the radiation fluid will always remain subdominant. Okay. So if it dominates, then suddenly it will become radiation dominated. But for 60 folds, at least you need to have your radiation fluid to be subdominant.
Yeah. So my question is whether you are tuning like the tuning there.
No, it's not a fine tuning problem.
But Well, okay, I still
Because see, if you have
we can
to,
discuss later.
even maintaining a this subdominant radiation fluid, you have to dissipate a lot, right? Because the radiation fluid is always diluting away with an exponential rate, and you have to keep on pumping energy to the radiation fluid so that you can maintain a radiation fluid, right? Unless and until your potential is potential energy is decreasing, you will not have a graceful exit, or you will not have a radiation domination at some point of time, okay? So when this condition is met, epsilon v is equal to 1 plus q, you will also see that your potential energy is falling over your radiation energy density, and at this point your radiation energy density will tends to take over.
Yeah, thank you. Please discuss with me later.
Okay, I have one comment and two questions. You referred to the sociological aspects of citations regarding cold and warm inflation. That's the comment, and I have a follow-up question. Is that one of the challenges I face in understanding warm inflation is how do I calculate the spectrum?
Yes.
I do not know personally of a very clear place where the spectrum is derived very
Yes.
unambiguously.
Yes.
And conceptually, I see there is a radiation involved.
Yes.
There is another fluid involved. There will be, for instance, isocurvature
Yes.
perturbation in some
Yes.
simple, even in the simplest of cases.
Yes.
I haven't seen a clear discussion
people-
of what happens to the isocurvature perturbation.
So-
These are the personal challenges I face
Yes.
in considering warm inflation.
Yes. So the thing is that as I showed you, the citation is very less. That means the field is very less explored. People haven't calculated isocurvature perturbation. There have been, now they have done the perturbation equations correctly, and there are review papers, and we are also organizing a school and a conference next year. Or you people are all welcome to come to Ashoka University, where there will be lectures on warm inflation perturbation
So
theory.
it's an open issue and it's
an
not
open
resolved.
issue,
That's my
and
point.
there is a lot of thing that needs to be done.
Okay, so the second remark is is related to what Kazu asked. I don't know what he exactly refers to as a fine-tuning problem, but whenever I have turned on the gamma,
Yeah.
and if you integrate your background equations, you will find that it is true that the radiation will be subdominant, but the energy density in radiation will jump significantly as soon as you turn on. So you start with some very small values. Maybe this is, I presume, the fine tuning is referring to. At least the range of gammas I've explored, it jumps. It remains subdominant to the inflaton, but I see that in other words, the transfer of energy from the inflaton to radiation is significant, and the radiation, acquires significant amount of energy even during the late stages of
Okay, we
inflection.
can discuss this later, but I have numerically evaluated all these background equations, but I have never come across this. I've never find
No, it will be subdominant,
Yeah.
but substantial.
But substantial, of course. That is the difference between cold inflation and warm inflation. And that's why I'm saying, as
And
we
it
have
becomes
also-
substantial, whatever small value of radiation I start with. This is my challenge.
That's right.
Okay, all right.
There will be
Okay.
substantial
So
radiation.
I thought my code was wrong. Okay.
No, there will be substantial radiation domination, but it will be dominated by your potential energy.
Any
Your
further,
radiation will not overshoot your potential energy.
any further
Hi.
quick questions?
Thank you for the very nice talk. I have a question regarding the hierarchy of this temperature of the radiation bath versus Hubble scales, because
Yes.
as you say, the radiation field should not redshift away, otherwise you don't have thermal equilibrium
That's right.
with
That's right.
the
So the difference between cold inflation and warm inflation is that in cold inflation, even if there is some dissipation and you maintain it, so the way you differentiate between cold inflation and warm inflation is in cold inflation H is always greater than T, and in warm inflation T is always greater than H. So your temperature, so this is the hierarchy. Okay.
One more question.
Yeah.
Is that in the standard cold inflation picture, we don't, we are interested in computing correlations of, let's say, curvature perturbations, and those remain frozen once they go super horizon.
Yes.
So we don't really care about what happens at reheating, how the inflaton decays to sand model particles. Here,
Here also the super horizon modes will be frozen.
So why exactly does it matter if, why exactly does the graceful exit matter? I mean, once it remains frozen super horizon,
No, you have to end inflation at some point of time.
yeah, but in the context of computing correlations, let's say I'm comparing it to
No, no, no. Even
proving
before going to perturbation theory and all, you have to end inflation, right?
yeah, but I'm still,
So in power law inflation, such as you can never do a graceful exit just with a standard mechanism because your epsilon is constant.